Afternoon, everyone. Today I want to talk about chargers. So this is the new topic that we're going to start talking about, and to kick it off, we're starting with electrostatics rather than full-on electricity. So electrostatics is the study of stationary chargers, so static, stationary. What we're going to be covering is the different types of surfaces that we really want to deal with, and the excess of one of these two things, which is going to determine whether it's this or whether it's this. So everything's got charges. So everything has protons and electrons. They also have neutrons, but neutrons are neutral, so we don't really care about them until we jump into term 4 and we're dealing with the nuclear stuff. The overall charge of something is determined by how positive or how negative it is. So if it's got too many protons, it's going to end up being positive. If it's got too many electrons, it's going to end up being negative. Now, here's two examples. So we have this surface over here, a lot of excess protons. This surface over here, a lot of excess electrons. So this would be positively charged. This one here would be negatively charged. Just because I haven't drawn any electrons on here, or just because I haven't drawn any negative charge, doesn't mean it doesn't have any. It just means that it doesn't have enough, and vice versa. It doesn't mean that it doesn't have any protons, it just means that it doesn't have enough. So this one here is 1, 2, 3, 4, 5, 6, 7, 8. Too many electrons, and this one here is 1, 2, 3, 4, 5, 6, 7, too many protons. Protons and electrons will always do this, attracting or repelling each other due to the electrostatic force. It's the reason electrons will actually orbit a nucleus in the first place. So there's positively charged things, protons, in the nucleus, and electrons sort of whiz it around the outside to varying degrees. So we have like charges repelling each other and opposite charges attracting each other. The size of the negative charge compared to the positive doesn't really matter. They're still consistent with the third law. So because we're dealing with the sizes of, the product of the sizes of the charges, it doesn't really matter if one's bigger than the other. So it's just like you are exerting an attractive gravitational force on the Earth, just like it is on you. Those forces are the same size because of Newton's third law. We know that they must be. It's just that, the Earth's got a little bit more mass than you and I. So here, the direction of the force is determined by the charges. So if we have a positive charge and a negative charge, we've got these two forces, one here, and they're acting towards each other. I should really have drawn these perfectly opposite and also the same size. If we have two positive charges, we have the forces drawn in this way. If we have two negative charges, we have the forces drawn in this way. When we are dealing with these electrostatic charges, or these charges in general, what we're going to be dealing with is conductive surfaces or non-conductive surfaces, so insulating surfaces. When we have a conductive surface with an excess amount of electrons or an excess of protons on it, the electrons will actually distribute themselves evenly across the surface due to these forces up here. So if we have too many protons, the excess electrons will be attracted to them. If we have too many electrons, the excess electrons will be repelled by them. So this repelling and attracting force will actually cause the free electrons, I guess, to wander around the place and distribute themselves, not like this. This is how it might start. You might have something negative over here charging this conductive surface negatively, and what will end up happening is these will start to move so that we have a more even distribution of this charge over the surface. Okay. Oops, no, I can probably come back here actually. So now we've got kind of the same amount of excess charge sitting all over the surface, but these electrons have wandered all over the place and moved themselves around, so that now it's more evenly distributed. When we have an insulator though, these excess electrons are stuck. An insulator means that charges cannot freely move, which means that these negative charges over here, they're stuck unless we physically move them in some way. So it might be by touching with a conductive surface, touching with your hand. That's how you end up with static charge builds up and on your socks when you're walking across a polyester floor or a nylon carpet or something similar, and then you can zap people with it because that's fun. When we have a charged object near an insulator surface, so let's say we have this charged object near the surface of an insulator, and I'll try and draw this without making too much of a mess of everything else. Cool. So there we go. So let's say here's our charged object, and here's our insulated surface, insulative surface. So this one here is something where the positive and negative charges can't move. So they're going to be fixed on this surface. Now, when I bring this near here, what we're actually going to do is interact with this surface layer. So just because it's a solid object and just because the charges can't move, it doesn't mean that in its own structure these two can't sort of flip and flip if the charges over here actually kind of entice them to. So in this case here, these two, we actually have negative stuff here and we have negative stuff here. So these two would actually kind of flip around like this, and these ones, they would also kind of flip. So now you can see the outside surface in this sort of region here is actually positive, which means that my round surface with a whole bunch of excess charge here is actually going to be attracted to this, because what we've done is force this surface to be oppositely charged, just like this one here. This is the idea that allows us to, pick up a piece of paper with a balloon when you rub the balloon through your hair. All right. What we're going to be dealing with is this distribution of charge on conductive and insulative surfaces, and how we can actually use this in real life to do some kind of cool stuff, but also make things move around more effectively. So before we get too far into this, what you need to do is copy this sort of stuff down, write some notes, so that we can dive into things like the Van de Graaff and have a hands-on experience, so to speak.